Myself, Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, we'll see some problems related to the nanotechnology. So, numerical problems on nanotechnology. So, the first problem, calculate the surface area to its volume ratio of a spherical particle of diameter 8 millimeters. So, the given data, that is particle diameter, that is spherical particle diameter has been given, and we need to calculate the surface area to its volume ratio. The surface area to its volume ratio. So we need to calculate the surface area to its volume ratio of a spherical particle. So here, particle diameter, that is spherical particle diameter d is equal to 8 millimeters. So we need to convert it into meters. So 1 millimeter is equal to 10 power minus 3 meters. So d is equal to 8 millimeters, that is equal to 8 into 10 power minus 3 meters. And from this, we are going to calculate the radius. So particle radius. So particle radius R is equals to d by 2. So 8 into 10 power minus 3 divided by 2 meters. So it is equal to 4 into 10 power minus 3 meters. So the spherical particle radius R is equal to 4 into 10 power minus 3 meters. So we need to calculate the surface area to volume ratio. So the formula for this surface area to volume ratio is equal to 3 by R. So where R is the radius, this formula can be obtained. This derivation of this formula we have seen already in the previous sessions. So that is taking a spherical particle and writing that surface area of the spherical particle divided by volume of the spherical particle. So when solving this two, we'll get, that is 4 pi r square divided by 4 by 3 by r cube. So that 4 pi r square into 3 by 4 by r cube. So here 4 pi gets cancelled. The r square gets cancelled. So we get 3 by r. That is, this is related to the surface area to volume ratio of a spherical particle. So that is why I have written here 4 pi r square. So surface area of a sphere, is 4 pi r square. So surface area of a sphere is equals to 4 pi r square, where volume of the sphere is equal to 4 by 3 by r cube. So when calculating surface area to volume ratio, of a sphere is equals to, so surface area of the sphere divided by volume of the sphere. So that 4 pi r square by 4 by 3 by r cube. So when solving this, simplifying, we'll get 3 by r. This is the surface area to volume ratio of a sphere. Surface area to volume ratio of a sphere. So that this like this surface area to volume ratio has been the 3 by r. So surface area to volume ratio of a spherical particle we need to calculate. So from the formula it is equals to 3 by r. So where r we know that 4 into 10 power minus 3 meters. So 3 by 4 into 10 power minus 3 meters when calculating we'll get 0.75 into 10 power 3 per meter. So this is surface area to volume ratio. So it is equals to 0.75 into 10 power 3 meters. Next one, if the radius of a sphere is made 1/3, how its surface area to volume ratio changes? So if the radius of a sphere is made 1/3, how its surface area to volume ratio changes? So the given data is radius. So radius is given, which is for a sphere. So sphere radius is made 1/3. So suppose if we take radius of the sphere, radius of the sphere r, here radius of sphere is made 1/3. So it is made of 1/3. So that or by 3 or is equals to r by 3. So this is the surface area, that is radius of the sphere. So this is the sphere and the radius of the sphere is r and it is reduced and this sphere is made 1/3 of radius. So that it is r by 3. So radius of a sphere is made of 1/3. How its surface area to volume ratio changes. So in this case, if the surface area to, that is if the radius of a sphere is reduced to 1/3, so how the surface area to volume ratio will be changed? So that we are going to solve. So the given data is radius of a sphere r is equals to r by 3, which is given, and surface area to volume ratio need to calculate. So for this we are using a formula surface area to volume ratio 3 by r, where r is the radius. So 3 by r. So this r is r by 3. So surface area to volume ratio formula is 3 by r. So where r we know that, which is given in the problem, r by 3. So 3 by r by 3. So it is equals to 3 into 3 by r, we will get 9 by r. So it is equals to 3 into 3 by r. 3 into 3 by r. So how many times it is increased? The surface area to volume ratio. That is, surface area to volume ratio is increased by 3 times. It's increased by 3 times. So that's why we are getting 3 into 3 by r. 3 into 3 by r. So surface area to volume ratio has been changed by 3 times of increase. If the dimension of a cube is double, how its surface area to volume ratio varies. So if the dimensions of a cube is double, suppose this is a cube. So dimensions of a cube means that we have, suppose this is A and this one A and this A. So the dimensions of a cube is doubled. Doubled means that two A. So dimensions of a cube is doubled, right? So we are getting doubled in the sense 2A. So in this case, how its surface area to volume ratio varies. So the given data is volume of a cube, a cube, that is equals to 2A cube. So surface area of a cube is equals to 6A square. 6A square. So that wherever A it is doubled, so that 6 into 2A square. 2A square. So it is equals to 6 into 4A square. So surface area to volume ratio, we know that surface area to volume ratio. So 6 into 4A square by volume of a cube is equals to A cube, that is 2A power 3. So it is equals to 24A square by 8A cube. So it is equals to so that we are getting 6 by 8. 6 by 8. So that here we have the surface area to volume ratio decreased by 2 times. Decreased by 2 times. So calculate average particle size using X-ray diffraction pattern having 0.154 nanometers of X-ray wavelength, 0.011 radian of full width and half maximum, and a diffraction angle of 45 degrees. So that the given data is wavelength of X-ray. Wavelength of X-ray lambda is equals to 0.1541 nanometers. So nanometers converted into meters. So 0.1541 into 10 power minus 9 meters. So full width and half maximum B is equals to 0.015 radians. If we take the full width, the half maximum, if for crystalline solids, we may get likewise the peaks are. So in this, we are getting this full width half maximum. This is full width half maximum. So this B is equals to 0.015 radians. And the angle of diffraction theta is equals to 45 degrees. From the formula Scherer's equation, D is equals to the particle size. D is equals to K lambda by B cos theta. So here K is the Scherer's constant. So for crystalline solids, it is around 1. For crystalline solids, the K value is 1. So it is equals to 1 into the wavelength 0.1541 into 10 power minus 9 divided by 0.011, which is this one is B value. B is a half width, full, no, sorry, a full width, half maximum. So 0.011 into cos 45 degrees. So we'll get the value 1.98 into 10 power minus 8 meters. Next one, a beam of X-rays is incident on a sodium chloride crystal with lattice spacing 0.282 nanometers. Calculate the wavelength of X-rays if the first order Bragg reflection takes place at a glancing angle of 8 degrees 35 minutes. 8 degrees 35 minutes. So the given data is lattice spacing. So lattice spacing means the interplanar spacing. As we know that lattice spacing in itself, so this is the crystal lattice. Crystal lattice, the line join passing through the lattice points gives the lattice plane. So lattice spacing means the interplanar spacing, that is the distance between the two parallel planes. Two parallel planes. So D value. So this is interplanar spacing or lattice spacing. So this is for sodium chloride crystal. So the lattice spacing or interplanar spacing D of a sodium chloride crystal is equals to 0.282 nanometers. So need to calculate, need to convert it into meters. So 0.282 into 10 power minus 9 meters. So the order of diffraction, is first order. So n is equals to 1. Order of diffraction n is equals to 1. And angle of diffraction. So Bragg's reflection takes place at a glancing angle of 8 degree 35 minutes. So that's why the theta value, so angle of diffraction or glancing angle, theta is equals to 8 degrees 35 minutes. When convert it into degrees, we will get 8.585. That is 1 degree is equals to 60 minutes. So in that way we are converting into degrees. So we will get 8.585 degrees. So the formula to get the wavelength of the X-ray. So Bragg's law, n lambda is equals to 2d sin theta. We may calculate lambda by using the Bragg's law, n lambda is equals to 2d sin theta. So from this, lambda is equals to 2d sin theta by n. So 2 into d, the spacing, lattice spacing, so 0.282 into 10 power minus 9 meters into sine of 8 degrees 35 minutes. That's it. So here 8.585 divided by order of diffraction is 1. Order of diffraction is 1. So that 2 into 0.282 into 10 power minus 9 into sine of 8.585 is equals to 8.419 into 10 power minus 11 meters. This is the wavelength of the X-ray, which gives Bragg's reflection at first order. Next one, X-rays of wavelength 1.5418 angstroms are diffracted by 111 planes in a crystal at an angle 30 degrees in the first order. So calculate interatomic spacing. Interatomic spacing. So the given data is wavelength and then crystal plane, then angle of diffraction, then which order it is. Then we need to calculate the interatomic space. So wavelength of X-ray lambda is equals to 1.5418 angstroms. So 1 angstrom is equals to 10 power minus 8 centimeters. So that is equals to 10 power minus 10 meters. So it is equals to 1.541 into 10 power minus 10 meters. So order of diffraction is n is equals to 1. Angle of diffraction is 30 degrees. So we need to calculate interatomic spacing. So interatomic space. D is equals to question. So we need to find the interatomic spacing. Okay. So from the Gross law, we can calculate the interatomic spacing. So n lambda is equals to 2d sine theta. So from this, d is equals to n lambda by 2 sine theta. D is equals to n lambda by 2 sine theta. So that is equals to so n is first order. So 1 into wavelength of the X-ray 1.5418 into 10 power minus 10 meters divided by 2 into sine 30 degrees. So we get 1.541 into 10 power minus 10 meters. So this is the interatomic spacing D. So next problem. An X-ray beam of wavelength of 3 angstroms is diffracted from 100 plane of a cubic crystal. The first order maximum is obtained for glancing angle of 40 degrees. Determine the space of the reflecting plane and also the volume of the unit cell. So the given data is wavelength and order of diffraction and then crystal plane and angle of diffraction. Angle of diffraction. But we need to calculate space of reflecting plane. Space of reflecting plane, that is interplanar space. Space of reflecting plane and the volume of the unit cell. Volume of the unit cell. But the type of crystal is cube. So we need to find the volume of the cubic crystal. Volume of the cubic crystal. Let's write the given data. So wavelength of X-ray lambda is equals to 3 angstroms. So 3 into 10 power minus 10 meters. Order of diffraction is first order. So n is equals to 1. Angle of order of diffraction is n is equals to 1. Angle of diffraction theta is equals to 40 degrees. But we need to find the space of the reflecting plane D value and then volume of the cube. Volume of the cubic crystal. So volume of the cubic crystal is a cube. So this we need to find. So for this we can get from the graphs. equation. So Gauss law is equals to n lambda is equals to 2d sine theta. So we need to calculate d. So d is equals to n lambda by 2 sine theta. So d is equals to n lambda by 2 sine theta. So order is 1. So 1 into lambda is 3 into 10 power minus 10 meters divided by 2 into sine of theta is 40 degrees. So we'll get 2.33 into 10 power minus 10 meters. So this is the value of D. So whereas we need to calculate the volume also. So volume of the cubic crystal. So AQ. So that is equals to. So here so AQ we need to find. So how we are getting that one is interplanar spacing. So interplanar spacing D. So we need to calculate interplanar spacing. From the interplanar spacing D for a plane. So we have the relation between A and D. So that interplanar spacing D is equals to A by root of H square plus A square plus L square. So it is equals to A by the plane has been given 100. Plane is 100 plane. So this is a H, K and L. So 1 square plus 0 square plus 0 square. So it is equals to A by root of 1. So it is equals to A. So D is equals to A. In the sense A cube is equals to D cube. So A cube is equals to D cube. So D is the value of 2.33 into 10 power minus 10 meters. So cube. So we will get 12.64 into 10 power minus 30 meter. This is the volume of the cubic crystal. Volume of the cubic crystal A cube is equals to 12.64 into 10 power minus 30 meter cube. So in an X-ray diffraction experiment, peak width at half maximum is 0.60 and its corresponding Bragg angle is 24 degrees. Calculate the crystalline size using Scherrer's equation. The wavelength used in X-ray diffraction experiment is 1.54 angstroms. So the given data is wavelength of the X-ray lambda is equals to 1.54 angstroms. So it is equals to 1.54 into 10 power minus 10 meters. So the value full width at half maximum B is equals to 0.6 degrees. When it is converted into radians, so it is equals to 0.01. So angle of diffraction theta is equals to 24 degrees. Angle of diffraction is 24 degrees theta value, and the Scherrer constant K is equals to 1 as it is a crystallite 1. So for crystalline solids K is equals to 1. From the formula to calculate the size of the crystallite. So from the Scherrer's equation, D is equals to K lambda by D cos theta. So D is nothing but to find the particle size. So K is nothing but Scherrer's constant, that is for crystallite solids, it is 1. So that is it would come 0.892 2.8 like that. So it become around 0.89. So that we'll take K value is equals to 1 for crystalline solids. So K is equals to 1. So D is equals to K lambda by B cos theta. So it is equals to 1 into lambda 1.54 into 10 power minus 10 divided by 0.01 radian into cos 24 degrees. So we after calculating we have the value 1.68 into 10 power minus 8 meters. What is the angle at which the third order reflection of X-rays of 0.79 angstrom wavelength can occur in calcite crystal 3.04 into 10 minus 8 centimeters of spacing? So the given data wavelength, so lambda is equals to 0.79 angstroms, so it is equals to 0.79 to 10 minus 10 meters. So order of diffraction n is equals to 3. So order of diffraction n is equals to 3. And the interplanar spacing is 3.04 into 10 power minus 8 centimeters. So this centimeters is converted into meters. So 3.04 into 10 power minus 10 meters. So angle of diffraction we need to calculate. So here we need to calculate the angle of diffraction. So that is what is the angle? So need to calculate the angle of diffraction. So formula Bragg's law. N lambda is equals to 2d sine theta. So from this, theta is equals to, so that is n lambda is equals to 2d sine theta. So n lambda by 2d is equals to sine theta. If sine theta is equals to n lambda by 2d, so theta is equals to sine inverse of n lambda by 2d. So what is the n? N is the third order. So sine inverse of 3 into lambda is 0.79 into 10 power minus 10 meters divided by 2 into interplanar spacing 3.04 into 10 power minus 10 meters. So we have after simplification the theta is 22.4 degrees. This is the angle of diffraction. Next problem. Monochromatic X-rays of wavelength lambda is equals to 1.5 angstroms are incident on the crystal face having an interplanar spacing of 1.6 angstroms. Find the highest order for which Bragg's law reflection maximum can be seen. So we need to calculate the highest order. So the data given is wavelength and then D value, interplanar spacing. So the given data, wavelength of X-ray lambda is equals to 1.5 angstroms. So that is equals to 1.5 into 10 power minus 10 meters. Interplanar spacing, D is equals to 1.6 angstroms. So 1.6 into 10 power minus 10 meters. So we need to calculate the highest order of Bragg's reflection, N is equals to. So for this, the formula Bragg's law, that is Bragg's equation, n lambda is equals to 2d sine theta. So n lambda is equals to 2d sine theta. So n is equals to 2d sine theta by lambda. So it is equals to 2 into d is 1.6 into 10 power minus 10 sine theta. So theta means that here didn't give the theta, but in the problem highest order for maximum reflection. So that 90 degrees we are taking. So Bragg's reflection maximum. So that we are taking angle 90 degrees. So lambda is 1.5 into 10 power minus 10 meters. So calculating this, we'll get 2.133 m is equals to. So it is nearly 2. So the highest order is 2. The Brock's reflection can be C. So the highest order of Brock's reflection is 2. So for this session, the reference books are Engineering Physics by K. Tyagarajan, Numerical Publications, New Delhi. A textbook of Engineering Physics, M.N. Avdhanilu, PG Sagar, H. Chandan, New Delhi. And then Engineering Physics by Dr. R. Muga and other publications, Chennai. Then Engineering Physics by P.K. Palanisamy, 4th edition, SciTech Publications, India Private Limited, Chennai, 6 lakhs. So these are the references related to the nanotechnology problem solvers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.